Hello, today we are going to discuss such a very important point as nuclear chemistry. The development of the science of chemistry is unimaginable without determining the composition of the atom and the composition in particular of the nucleus and the electrons that revolve around it. But the development of this branch of chemistry is inconceivable without the development of nuclear chemistry, because these experiments help to lead scientists to what exactly could be going on in the atom. This moment was preceded by several historical aspects. First of all, in the year 896. French scientist Henri Becquerel discovered by chance in experiments with uranium the element uranium 92nd and 238 of its mass, while casually conducting experiments, wrapped the remains of the uranium ore he was working with in photographic paper and placed this paper in his desk until the next day to be analyzed later. What was Becquerel's surprise when he discovered some time later that the photographic paper had been illuminated by extraordinary rays. Thus, the phenomenon of radioactivity was accidentally discovered. After a period of time, Polish scientist Maria Skłodowska-Curie and her husband Pierre Curie discovered that this phenomenon of radioactivity was not just confined to uranium, but to elements like polonium, as well as radium and also thorium. And for the discovery of the elements polonium and radium, Skłodowska-Curie, she was awarded the Nobel Prize in Physics and Chemistry. This is the only woman scientist who received 2 Nobel Prizes in different branches of science. With Pierre Curie, only one element, polonium, was discovered, which is named after the country, the birthplace of Marie Skłodowska-Curie. Radium was discovered already later. Then the key moment in the discovery of nuclear chemistry happened in 1898 year, when the scientist Ernest Rutherford conducted his remarkable, extraordinary experiment. In a special capsule were placed radioactive elements that emit certain rays. As these rays moved, electromagnets were placed. That is, the deflection of these rays in the electromagnetic field was studied. It turned out that some rays moved by being attracted to the minus pole. Such rays were called alpha rays. Then there were rays that moved toward the positively charged electrode. These rays were called beta rays, and rays that did not veer to either side were labeled gamma rays. Thus, scientists, and Rutherford in particular, concluded that when radioactive elements emit rays, these rays can have a certain directionality, with the exception of gamma rays. And what these rays turned out to be, what they consisted of. Now, the first rays are alpha, land-abled alpha. And it turns out, when you start to work out what it is, it turns out to be the nucleus of the element helium. And the number is 2, in this case nuclei, so plus 2 and 4. It was because these nuclei had a positive charge that they were attracted to the pole of the minus magnet. Next, there are rays that are labeled beta. These rays, sometimes called cathode rays, are labeled electrons. So it turns out that they are electrons and their charge is -1, but the mass of the electrons is very small, about 0. Now, the most complex rays that didn't deflect anywhere are gamma rays, but gamma, that's ours. It turns out it's not a particle. Unlike alpha and beta, which are specifically particles, and beta, which we've shown is beta rays minus, and then there's beta rays plus, that's positrons, and in this case, gamma turned out not to be particles, it turned out to be radiation, so it's not particles, and gamma rays are the particles that are labeled. And this radiation has both a mass of 0 and a weight of 0. Such rays turned out to be very hard, and if you express it in hertz, it is a wavelength of 10 to the 20th hertz, which corresponds to a wavelength. You get less than 1 peak meters. These rays and these particles themselves have different penetrating effects. We will talk about this in more detail in the next lesson, but now I would like to say that alpha rays can be delayed even by an ordinary piece of paper or the palm of your hand if you put them in their path. If they are beta rays, then to delay them, you need either a copper plate 1 centimeter thick or by analogy an aluminum plate, but the most dangerous are gamma rays because such radiation can only delay lead, and that is very thick. So these rays are the most dangerous for us. But it was later in Rutherford's famous experiment that it was discovered that amongst of the rays and particles that could still accompany these processes, there could also be beta rays. Beta rays which are made up of positive value, then such rays would be deflected in the other direction, and these are electron particles, but only they would have a charge of +1, 0, not minus, and this particle is called a positron. In addition to that, sometimes nuclear reactions can involve neutrons with a charge of 0 and a mass of 1, and protons with a charge of +1 and a mass of 1. Now, very often, some quite active isotopes can participate in nuclear reactions. For example, such an isotope is deuterium, which, as you may recall, is an isotope of hydrogen that has the number 1 and mass 2. But the most active isotope is isotope 3, which, as you know, is hydrogen, which has a mass of 3 respectively. That is, in addition to the experiment which was conducted directly by Rutherford, there are other particles that can also be obtained in nuclear reactions or conversely bombard such nuclei or such atoms to get different elements. The discovery of nuclear chemistry played an enormous role because there's a lot of energy being generated. For comparison, if you take 1 gram of methane, for example, you can get, in this case, 57 kilojoules of heat. But if we take, for example, 1 gram of uranium, which Beccarius worked with, the amount of energy is millions of times more, so nuclear energy is very, very high in that regard. And we will talk to you about the characteristics of these phenomena of this particle and radiation in the form of gamma rays in the next lesson, where we will give specific characteristics and specific nuclear reactions, and we will see how such nuclear reactions are formalized in practice, and we will learn to predict the products of such nuclear reactions. Don't miss our next lessons. Goodbye.